we do any earlier than Friday just before midnight. So you'll have around 2 days to do it. Anything else? So don't hesitate to put more questions in the chat. Sorry. As time goes on, but I will turn it over to Carl now. So I'll stop sharing. Okay, Carl, your turn.
Okay, it'll take me just a moment to get my bearings here. I would need to share my desktop. I hope I'm recording right now, so we can post this later. Okay, so can I get some confirmation that anybody can see this? If you could just say in the chat, can you see my
Yep, you got some people, we can see you.
Oh, good. Okay, and now I can see the chat window, so that's really good. Thank you for the response from Nathaniel, Sarah, Casey, Cassandra, etc. Thank you all. Okay, so what I'm going to try to do here is we'll pick up where we stopped last time. I hope you don't mind my backdrop here. This is a picture of Demerit Hall, just to make you, oh, and you can see the sheet behind it all. This is Demerit Hall. It's the only picture that I had of it is of my kids defacing the blackboards. We had a little bit of a talk last time about whether I should use a backdrop or not. People sent me some things. Here's the one that people sent me, was some kind of monster. I don't know if that's good or not. And can you increase the size of your PDF again, please? Yes, I will. So let's try that. Sarah, is that sufficient for you? And Hans says that is velociraptors. Okay. So what we did last time was Coulomb's law, and just reminding you what it was, we have this kind of slightly complicated equation where we have the force is given by the magnitude of the two charges involved, Q1 and Q2. They're separated by some distance r, and the force is going to be given by Q1 times Q2 divided by the distance squared. And the bookkeeping device that gives us the right numerical answer is going to be Coulomb's constant, 9 times 10 to the 9 Newton meter squared per Coulomb squared. The last part of understanding this is that for two like charges, either plus plus or minus minus, this is going to be a repulsive force. They're going to push apart from each other. If this is opposite charges, a plus and a minus, then they are going to want to be attracted to each other like that. So we'll get a good example of that in a moment for that. Before I get to that example, let me show you what's going on. Okay. Yep. Yes. Let me get to the demo that I want to show, and that is of Coulomb's law in action. So let me start this over, and I remind you again, Coulomb's law. Let me see if I can get this in the background. Now what I'm going to, from the earlier lecture, what I realized is I'm going a little bit faster with my lecture than I would have as I was writing on the board. I'm going to count on you guys to please tell me to slow down or to wrap back and show something if I go too fast, because I don't have that natural deceleration of having to write these equations on the board. It's the reason I never use PowerPoints when I'm lecturing, is because I go too fast. And until we figure out some way that I could actually write equations for you guys to watch in this virtual thing, I'm going to probably have a tendency to go faster than I would like and that you would like. So please, in the chat, just say slow down or loop back to the previous slide. I'm happy to do it. Here's our Coulomb's force. I'm looking at a demo here that evaluates the magnitude of the force between these two objects. So what happens when we have no charge on either of these, 0 coulombs? Well, I have a 0 here, I have a 0 here, the net force is 0. what's interesting is if I have a charged object here, I can increase this charge, say it's, and this symbol here is Greek mu. It stands for 10 to the minus 6. It's micro in SI. It's 10 to the minus 6. So this would be 4 times 10 to the minus 6. The actual numbers here, please don't get hung up on them. They don't matter. I just want to give you some demonstration of this attractive and repulsive ability of this force. So I put a positive charge on this guy, and what happens? There's still no net force. It takes charge on both of them for there to be a net force. Now I put some charge on this guy, I put some charge on this guy. You can see the force arrows coming out here, and they're equal and oppositely directed. This is a repulsive force, so they're going to be trying to get away from each other. And if I bring them closer, that 1 over r squared, the distance in the denominator, means that that force grows very strongly as you decrease the distance between them. You can see those arrows getting bigger, bigger, bigger. If the other side of the coin is if I have one of them positively charged, one of them negatively charged, and in this case, I get an attractive force, positive and negative. They are going to want to be attracted towards each other. They're going to be drawn towards each other. And again, we can see that 1 over r squared behavior as they approach. So, okay, if that's okay, I'm going to move on. That's just a review of what we did last time. So what I want to talk about now is charging an object. So we talked about how do you come up with, in the world around us, my hands, this desktop, the velociraptors behind me are net neutral objects. They don't have any net positive or negative charge. They're charge balanced. So, all right. So, so how do you wind up with a net charge on these objects? Well, you can do this by stripping out electrons. And let me see if I can get my demo back up here again. So what I want to do is, let me reset everything here. So I have a balloon here. Let me remove the wall for a second. I have a balloon, and I hope that you guys can see this. Please in the chat, let me know if there's any problem viewing this. So I take my balloon and I bring it over to my ugly sweater, and I rub the balloon against the sweater, and it's stripping off electrons just by friction. Just by friction. It's that easy to strip electrons out of this. And we wind up with a net distribution of electrons on the balloon and a net positive charge on the sweater. So what we have here is two oppositely charged objects. This balloon's going to be attracted to that ugly sweater. So what we do now, let me try another balloon, come in and steal some more electrons off the rest of the sweater, so that now the sweater is all positively charged and I have two negatively charged balloons. These two negatively charged objects are going to repel each other, okay? So we have, first we have the attraction of this balloon to that positive sweater, and we have the repulsion of negative to negative. The last bit of this that I want to try to show with this demo is if I have a wall here, and I'm not going to remove any electrons from this wall. It's a charge balanced wall. There's as many positive and negative charges on the wall. But let me charge up my balloon, get it very negative here so that it has a lot of negative charge. And as I bring this negative charge over to the wall, this is grossly exaggerated from what's happening, but you can imagine that the positive and negative charges in the wall, the protons and the electrons, are going to be displaced ever so much because there's a repulsive force between these electrons on the balloon and the electrons in the wall that move them. They'll tend to move a little bit further away, and the positive charges will tend to move a little bit closer, even though the wall stays net balance charge 0. But you have a little bit of a displacement of that positive and negative charge in space. The negatives are getting a little bit further away. The positives are staying where they are. We call this phenomenon polarization. And we'll come back to this again. It's actually a really neat phenomenon. So in the end, we can polarize that wall by pushing the electrons further away, the negative charges further away from the net negative charge on this balloon, and the positive charges stay where they are. And in the end, this could actually create a force between these, even though that wall is net charge 0, but we have a displacement of those charges. This is a very subtle difference from what I showed before with this guy. This was talking about point charges, and if I have a point charge with no net charge on it, then that charge is 0 and your force is 0. This is a slightly subtler phenomenon where you still have a charge 0, but you've displaced the positive and negative balancing parts of it, and you could result in a net force. Okay, so if that's okay, I'm going to push ahead. If not, please do. Why don't protons move when the positively charged object comes to the wall? Excellent question. So Fran Gessel asks, why don't protons move when a positively charged object comes to the wall? The answer is, this is I'll give you this answer in two parts. One is, this is a silly cartoon and it's not really realistic. First of all, the displacements that we're talking about are on the level of, you know, milli-angstrom. So some small fraction of an angstrom is going to be how much these displace. And if you recall, the more complicated answer is, if you recall when I talked about protons and electrons last time, the proton is about 2,000 times heavier than the electron. It's just easier to move the electron. So you will, as always, you would have some net displacement of those positive charges. It's not shown in this cartoon. Your skepticism of the cartoon is entirely well-founded, and it's a good question. But I think it's, you know, the effect is quite small. So our three, you know, just to summarize our three observations that we just made with this balloon experiment: our like charges repel, our opposite charges attract, and this neutral wall could become attracted to a charged object because of this phenomenon of polarization. Okay, so I'm going to push on unless there's any other questions. And again, please do, even if you just type the word slow into the chat, that will cause me to slow down or rewind the slides. Don't hesitate to do that. Can you go back to those three observations? Absolutely. And while I'm going back to those three observations, as a request from the earlier class to post these notes online before lecture, I will absolutely do that as soon as I get my act together to have these ready before lecture, so that you can actually not waste your time kind of trying to write down what I'm writing. If you so want to do so, I will post these going forward. I'll try to post these before lecture so that you have them ahead of time. So the three observations: like charges repel, opposite charges attract, and a neutral object can become attracted to a charged object because it becomes polarized. Okay, I hope that's enough time. Thank you. Thank you. Yes. Okay, Jacqueline, and we'll move forward. And thank you for letting me know. I really do need that kind of pacing on this, because this is all new, and I will tend to go too fast if you don't tell me. So I appreciate that. So our idea now is, we dealt with forces in the first semester when we were dealing with Newton's laws, and we learned that force is a vector quantity. Electrical forces are no different from other forces in the sense that they will add as vectors. So this is, I'm going to put this kind of very abstract. Let me wind down here so that we don't get distracted by the next bunch of words. If I have multiple forces, they're going to add vectorially. So I have this arrow on top. If I'm trying to find the net force on an object, then what would I would do, and let's say that object is object J. I'm sorry that this is so abstract, but think of J as a number like 17 or something, and that's the index that I'm referring to this object that I want to think about the forces on. So the forces from 1 on object 17, plus the force from 2 on object 17, plus the force on 3 on object 17. I get it that this is way abstract. I'm going to try to explain this a little bit better with an example. But the idea is, our J is the point of interest where we want to figure out what the force is. And each of these 1, 2, 3 are the multiple charges that could be acting on that object. So our example two charges, two 10 nanocoulomb charged particles are 2 centimeters apart on the x-axis. What is the net force on a positive 1 nanocoulomb charge midway between them? And we're hitting about the midway point of the lecture. I'll leave this right here so you guys can see it for a moment. Dawn has asked me to pause or stop the recording midway so that we get smaller videos to post online. So if you'll bear with me, I'm going to stop the